Hello to you, inquiring minds. In this video, we're going to identify 7 physical properties of our home planet, Earth, so that we can compare and contrast those with the physical properties of other planets and solar system objects in future videos. In this course, we will define a planet as an object that revolves around or orbits a star, is large enough that its own gravity forms it into a sphere, and does not have any similarly sized objects within its orbit. Astronomers who focus on studying the planets and other objects in the solar system are called planetary scientists. Planetary scientists study and work to measure and compare the physical properties of planets and other solar system objects. To begin our journey into the world of astronomy, we will focus on just 7 physical properties. In this video, we'll use the only planet that anyone has ever visited in person, Earth, in order to illustrate these 7 physical properties. We start with Earth because you should be most familiar with this planet and its physical characteristics, since it is the planet on which you live. Here we are at Earth. The first physical property we will look at will be the size of Earth. Now, size can mean many different things for planets. It could be its volume, or circumference, its mass, etc. Just like we did for the Sun in our scale model of the solar system, we will use the diameters of the planets and other solar system objects to compare them with each other. If you remember from our previous video, or math class, the diameter is the length of a line that goes from side to side and passes through the center of a circle or sphere. The Earth has a diameter of approximately 7,918 miles. If you were able to drill a hole straight through the Earth and out the other side, that hole would measure about 7,918 miles long. In the graphics and the chart in your astronomy journal, you will see that I list the size in both miles and kilometers. Most countries around the world use the metric system. Because of this, you will often see metric units used in science information since it's shared around the world. In these charts, we are also using the imperial unit of miles to give you a better opportunity to visualize the size of these planets in your head. Some of you may have participated in a 5K before, and could have a concept of how far a kilometer is. But I know all of you have participated in the mile run in gym class. To give you a reference that's a bit larger in scale, the United States is approximately 2,500 miles from coast to coast, or about 4,000 kilometers. The next physical property we will learn about are the average distances planets and other objects are from the Sun. The reason it's the average distance is because planets and other objects do not go around the Sun in perfectly circular paths. The paths that planets and other objects travel around the Sun, or what we call orbits, are slightly oval. We do not notice it in models, such as this, because at this scale, the oval would be so slight that the difference from the furthest and closest points is not noticeable by your eye. At its closest distance to the Sun, which occurs in the first week in January, the Earth is about 91.5 million miles from the Sun. At its furthest distance from the Sun, typically around the 4th of July, Earth is 94.5 million miles from the Sun. To find the average, we add the two distances together and divide by 2 to get an average distance from the Sun of approximately 93 million miles. Like we talked about in a previous video, space is big, and even units like millions of miles aren't a big enough measuring stick in space. We talked about how far light can travel in a certain amount of time and can be used to measure very large distances, like light minutes or light years. In our solar system, astronomers will often use a unit of measure called an astronomical unit, or AU. An astronomical unit is the average distance from the Sun to the Earth, or approximately 93 million miles. This unit is also included in the data we will be looking at, and will be useful in comparing and contrasting objects in our solar system. The next physical property, rotation period, is the amount of time that it takes an object, like a planet, to spin one time around its axis. If we imagine a line running straight through the Earth from the North Pole to the South Pole, that would be the axis. The Earth completes one rotation or spin around that axis in just about 24 hours. This is the period of time we call a day here on Earth. As each planet completes one rotation or spin, that would be one day on that planet. To give you a better understanding of how long it takes that planet to complete a single rotation, we report the time in Earth days. The orbital period, on the other hand, is the time that it takes the object or planet to orbit or go around the Sun one time. The Earth's orbital period is approximately 365 1/4 days, which is what we call a year. We can also say that the Earth will rotate or spin 365 1/4 times each time that it goes around the Sun. Now you may say, but a year's 365 days. What about the 1/4 turn? And that would be very observant of you. That is where leap years come in. Every 4 revolutions around the Sun, or years, we add up those 4 1/4 turns into one whole turn and add in that one day as February 29th. This is what is known as a leap year, with 366 days in it. Leap years occur just about every 4 years. The density of an object is a measure of how much mass, or stuff, is packed into a given volume or space. As an example, this kickball that we used as a model of the Sun is just about the same size or volume as this bowling ball. But the bowling ball has much more mass or stuff packed into that same volume. So we say that the bowling ball is more dense than the kickball. The units for density is read grams per cubic centimeter. This is just how many grams, which is a measure of mass, would be in the volume of a cube that measures 1 centimeter by 1 centimeter by 1 centimeter. Next we come to the average surface temperature. Notice that we use average here again, because the temperature of any planet is not the same everywhere on the planet all the time. For example, here on Earth, we have very hot regions around the tropics and very cold polar regions. It can be warmer in the sunlight during the day and cooler at nighttime. If we take multiple temperature measurements from around the world at any given time and find their average by adding them all together and dividing by the number of temperatures we measured, it will usually come out around 59 degrees Fahrenheit. We all know that it's not 59 degrees everywhere on the Earth all the time. That is just the average. The charts that we will be looking at will also include the extreme hot and cold temperatures expected on the surfaces of the planets. When we get to the larger planets of Jupiter, Saturn, Uranus, and Neptune, these expected temperatures get a little tricky because those planets don't really have a surface to measure temperature at. But we'll discuss that a bit more when we get there. The last property of each planet that we will look at isn't exactly a property, but more of a characteristic. This is any moons that may be orbiting the planet. Some planets have moons and other planets do not. Some planets have a few moons and some planets have many, many moons. In the beginning of this video, we defined a planet as an object that revolves or orbits a star, is large enough that its own gravity forms it into a sphere, and does not have any similar sized objects within its orbit. A moon, on the other hand, is a naturally occurring object that revolves or orbits around a planet or any other object that is not a star. There is some debate still among astronomers about how big an object may need to be for it to be considered a moon. The Earth just has one moon that we call the moon, or sometimes Luna. It can be confusing since we have a moon named Moon. When you are writing about a moon around another planet, it gets a lowercase m because that is a common noun that is a generic person, place, or thing. But when you talk about the moon, the bright thing that we can see in the sky from Earth, it gets a capital letter because it is a proper noun that is a specific person, place, or thing. To be fair, when we named the moon, we did not know there were other moons out there. The Earth just has one moon that we call the moon, or sometimes Luna. The moon that orbits the Earth is unique compared to all the other known moons in our solar system because it is large for our planet. Many other moons that we have observed are very small when compared to their planets, at most 5% the size of their planet. Our moon, the moon, with the diameter of more than 2,000 miles, is about 27% the size of Earth. As we will learn later on in our unit, this large relative size of the moon to the Earth affects our home planet in some interesting ways. In our next video, we will visit the 4 planets closest to the Sun in our solar system and try to understand what they are like by comparing and contrasting them to the physical properties of Earth that we looked at today. Until then, remember to look up, be amazed, and be excellent to each other.